Welcome, we are going to obtain the frequency response of a single degree of freedom system with these properties. At first, in part module, click on create part. Then in the dialog window, in front of name, type a name, for example, mass. And from this part, click on point and then click continue. Now in this part, type the coordinate of the point, for example 0, 0, 0, and then press enter. Now we change the part module to the property module. Then click on special, inertia, and create. Now in the window, click on point mass and then click on continue. In this part, select a name for the point, for example set point, and then click on the point and then click on done. In front of this part, type the mass 2 and then click on OK. Now change the property module to the assembly module. Then click on instance part and in the dialog window, at first select the mass from this part and then click on OK. Now change the assembly module to the step module. Next, click on create a step and in the dialog window, in the procedure type, select linear perturbation and then click on SDOF dynamics direct and then click on continue. In the dialog window, in this part, type the lower frequency, for example 0.01, and in this part, as the upper frequency, type for example 1.2, and for the number of points, type for example this value. It should be noted that the values in this part are in hertz, and then click on OK. Now, in order to edit the field outputs, click on Field Output Manager. In the dialog window, at first, click on Created and then click on Edit. In the dialog window, deselect stresses, strains, and forces. And then click on OK. And then click on Dismiss. Now, change the step module to the interaction 1. Next, click on Special, Springs Dashboards, and Create. In the dialog window, click on Connect Points to Ground and then click on Continue. In response to select points to connect to ground, click on Sets and then click on Mass Point and continue. In the dialog window, in this part, select 1 as the degree of freedom of spring at dashboard, and then in front of spring stiffness, click and type 4. Then activate this part and type 1 as the dashboard coefficient, and then OK. Now change the interaction module to the load module. Click on Create Load. In the dialog window, type a name, for example load 1, and from this part select step 1 and then click on concentrated force and then continue. In the dialog window, click on mass and then click on continue. In the dialog window, in front of CF1, type 3 and type 0 and 0 for CF2 and CF3 and then click on OK. Then change the load module to the job module. Next, click on Create Job. In the dialog window, type a name, for example 1, and then click on Continue. The dialog window, in the Memory tab, in this part, type for example 100% and then click on OK. Now click on Job Manager in the dialog window. In order to start running the job, click on Submit and wait for completing the job. As you can see, it has been completed, and in order to open the ODB file and see the results, click on Results. Now click on Result Options and click on Complex Form tab and select Magnitude and then OK. Now click on XY Data and in the dialog window click on ODB Field Output and then Continue. In the window, from this part, select Unique Nodal and then click on Magnitude and then click on Elements Nodes tab and click on Node Sets, then click on Mass Point and click on Plot. In order to close the window, click Dismiss. The displacement frequency can be seen, then double click on this part and in the window select this part and this part and click Dismiss. Now we can compare the results with the results obtained from the vibration theory. According to the vibration theory, the undamped natural frequency of the system can be found from this equation. Omega n equals 1.4 and it can be found in hertz from this equation. And the damped natural frequency can be found from this equation. It is 1.39 and the natural frequency can be found in hertz from this equation. Also, the frequency response can be found from these equations. The displacement frequency plot has been shown in this part. As you can see, the results are the same. Now click on Result, Options, and from Complex Form, click on Phase Angle, and then click on OK. Now click on XY Data, and from the window, click on ODB Field Output, and then Continue. In the window, choose the magnitude of displacement, and then click on Elements Nodes tab, and then click on Node Sets. Now click on Mass Point and click on Plot. As you can see, the phase angle frequency plot has been shown. Now we can compare the results with the results obtained from the vibration theory. As you can see, the results are the same.